See, here I am writing a command equal to lom SINV this command is generating standard normal random number, and these random numbers are white noise. This means that there is no autocorrelation, no heteroscedasticity, and zero mean among these. There is some spelling mistake, I guess. I should write RAND. I am dragging this down, and if I plot this series, you can see the series is in between +1 and -1 for most of the observations, and some of the observations are beyond this limit, and they are usually between +2 and -2. Means in the beginning of the data and at the end of the data, you have same spread of the series. This is same variance throughout the data, and you cannot see any pattern in this. Now let me generate one more series out of this. I am writing here equal to A1. This is basically, if you put a title on this series, it could be epsilon t. Epsilon t. Now I am generating yt. One beauty of using this command to generate data is whenever you are making any change in the Excel sheet, the entire data will be regenerated and you can see the second graph. For example, see, here I am making graph. This is the graph I have made. Now I am writing here 1. I have made some change, the entire data will regenerate. It should change automatically. ये क्यों नहीं change हो रहे अभी? Yes, that's all right. But yeah, if you are pressing this delete button anywhere in the Excel sheet, all of the data will be regenerated and you can see the second graph. But whenever you are making a new graph, this is basically new simulation. What is simulation? For example, you have a dice in your hand and you are throwing it again and again. Every time you throw the dice, this is a simulation. And in similar way, this is also a random experiment. Whenever you are making any change or pressing the delete button, all of the data is regenerated. This is a new simulation. And whenever you are simulating, you can see the data is having roughly same spread throughout the data, throughout the series, and you cannot see any particular pattern in this data. You cannot predict second observation on the basis of first. Now let me generate the second series out of this. I am writing here yt is equal to 0.9 multiplied by yt minus 1 plus et. Now I will follow this formula. The first observation can be copied directly. I am copying this A1, I2, and next. Now the next number is bound with the first. I am writing here equal to 0.9 multiplied by the first observation, which is J2 plus ET. E is epsilon, and epsilon is coming from the column I. And now I am copying down this data to the end. And let me make the graph. I have written this 0.9 multiplied by J2. We are in cell J3, and J3 is bound with J2. 0.9. This is arbitrarily chosen. You can choose any other number as well. But what I want to do, I want to generate stationary series, and the stationary series should have coefficient less than 1. So you can choose any number which is less than 1. Right. Now let me look at the graph of this series. This is your graph, and what is the difference between this graph and the previous graph? Basically you can see a very strong pattern in this. Where is the pattern? For example, if you look at observation number 19 up to 34, all of these observations are positive. And if you see the observation number 2 up to 11, up to 13, all of these observations are negative. This means if I am seeing an observation, it is positive, I will predict the next observation is also positive, and I am correct in my prediction most of the times. Sometimes I can make mistakes, but the frequency that I will make correct prediction is much larger, and the frequency that I will fail is much smaller. So in the similar way, you can see here from 34 up to 40, all of the observations are negative. This means I can make 6 correct predictions, and then I will make 1 false prediction, and then you can continue with this pattern till the end. This is this data is having autocorrelation. इसको क्या हो गया? This data is having autocorrelation, but because we have chosen the rho is less than 1, so the spread of this data will remain roughly same. The variance will remain roughly same. Here the data, most of the data is between +3 and -3, and if you go to the end of this data, it is again between +3 and -3, and these are 80 observations. If you make 800 observations out of this series, you will see that entire data will remain in this boundary. It will be between +3 and -3 most of the times. Okay. Now in the next column, I will generate the unit root data. What is unit root? Let me tell you. Here I am writing yt equal yt minus 1. I haven't written any other coefficient as a multiple of this. So this means the coefficient is 1 plus et. So how I will make this series? Equal to I2, and then the next is bound with I1 equal, this is equal to K2 plus I3. K2 is the previous observation plus I3. And let me copy this data down, and let me make the graph. Now you can see the pattern is very strong now. You have very strong clusters of positive and negative observation together. And the second thing is, this series can go arbitrarily away from the mean. It is not necessary for this series to come back to origin. Sometime it may come, but sometime it may not come back to the origin. This is going away from origin for a very long distance. This is because this series is having the formula for variance of this series is T sigma square. If T is going up, this variance will also go up at a linear scale. T is going like this 1, 2, 3, 4, 5, 6, and the variance will also increase in this space. Now let me make an explosive series. How I can make explosive? If I am putting the coefficient coefficient greater than 1, it will become explosive. So let me see how the explosive series is behaving. Here I am writing yt equal 1.2 multiplied by yt minus 1 plus epsilon t. Because the coefficient is greater than 1, this will become explosive. Let me see how this series is behaving. I am writing here I2, and then next is 1.2 multiplied by the previous observation L2 plus I3. This has become explosive. I will copy this formula down. Let me